We'll start off with a short course by Bill Hart on short division.
Those of you who were at the last meeting I was at know that I discussed polynomial multiplication, and I displayed a graph illustrating the speed difference between FLINT, which is the package that I'm working on with David Harvey, and Magma. So here is the updated graph since we rewrote FLINT. Last time I showed you this graph, there was a fair bit of red in this area, and I think some up in here. The brightest points on here were 3 times faster than Magma.
Is that division or multiplication?
Sorry, this should be multiplication. I haven't had time to change the configuration file, but this is definitely multiplication. You see the division graph later looks quite different. Okay, so yeah, basically polynomial multiplication is 3 plus times faster than Magma at some points, and the black regions are basically where we break even with Magma. So I thought I'd just begin by updating.
What are the active here?
Sorry?
The number of
Oh, sorry, yeah, okay. So they're labelled, but it's log base 2 times by 10.
This is not plotted, yeah.
So this is actually going up to 16 million, the polynomials of length 16 million, and this is coefficient bit size up to 16 million. Obviously, anywhere out in this region is going to take too long to compute, so we don't.
Which representation of polynomials in FLINT are you using for this?
This is FMPZ.
Which can you remind me which one that is?
That's the one that you want to put into Sage at the moment.
Yes.
So it's where the coefficients can have a whole bunch of different sizes?
No, this is the one where the coefficients are
All the same amount of memory?
yeah,
Okay.
all the same. Yeah. So this is just for uniformly distributed random numbers.
Perfect.
So with positive
And the
coefficients.
bluer the dot, the better FLINT is? Or?
That's right, yeah. So black,
And the redder
black is
the-
where we're breaking even with Magma, basically. I mean, these are not actually perfectly black. I mean, there's no red here at all. But the blue dots here, for example, and up here are about 3 times quicker, at least. In fact, I think it's up to 6 in some points.
And you're
So-
never slower.
Not in this graph. I have another graph from another machine where we haven't tuned FLINT, and there's some red dots here. There's a couple of red dots there.
Is this sage.math, this machine?
This
that
is
you?
Sage.math,
Okay.
and this was done today.
It's
Oh,
hard
cool.
to say exactly what's going on right at the bottom left because there's this interpreter overhead.
Mm.
Yeah, so down
Sure,
here,
sure.
Magma's at a severe disadvantage. Probably in this circular region, you can see Magma's at a severe disadvantage. We do try to subtract the overheads. We actually run everything except the multiplication in Magma and subtract that time to be fair to Magma.
You should ask Alan Steele for a special function that runs all in the same
Just
level.
this.
Exactly. The benchmark you need.
Yeah, if he provides me with a source code, I reserve the right to reverse engineer it. Okay, so anyway, that's enough polynomial multiplication. It wasn't what I wanted.
It would just return instantly.
No, that's the point of that. So let me just give you a very quick status report on where FLINT is actually at, because I think the perception is that we only have polynomial multiplication. So we have a highly optimized quadratic sieve for factoring large integers, and it is now on a 64-bit machine for anything less than or equal to 71 digits. It is faster than or equal to MSIV, which is pretty much indisputably the best implementation out there. So we're gradually winning. But this is only on a 64-bit machine. I still haven't managed to beat him on a 32-bit machine.
My understanding is it's just like blows away Perry, Magma, and
Sure,
Maple.
it's
mathematically.
about 5 times
Magma
faster
doesn't
than
look very
Magma,
good for
and
that.
about 8 times
Okay.
faster than Perry.
And
on this machine.
I'm not familiar with the current state of number field set, but below 71 decimal digits,
Yeah.
quadratic sieve is the method of
The
choice.
optimal one, yeah.
Probably
So,
100 or 100.
Because multi-polynomial.
once you get to about 90 to 100 to
Yeah.
110, depending on who you
That's-
speak to, that's roughly
Yeah,
the
yeah.
crossover. The reason we're not winning after 71 is because MSIF uses hash tables, which I'm about to implement, and also the double prime variant, which I'm about to implement. And it's probably feasible with a triple prime variant to go up to about 110 digits.
Wow.
And then you really have to have another field sieve. But this is already talking about days of computation to factor a single integer. So.
Is there anything, do you have any remarks to make about adding a number field sieve implementation to Sage?
Yes, I'd say just add MSIF. I think it's probably nearly at the point where it will.
And you can build it on a wide range of machines? Or are there serious issues with that with MSIF?
He's removed the reliance on GSL, and I think he's got drop back routines in C for everything now.
Okay.
So,
And so MSIF does
it's
both.
best to ask him.
It does both quadratic sieve
It does
and
both.
number field sieve.
Yeah,
Okay.
it does both. I mean, eventually we want to replace the quadratic sieve with this because it'll be quicker. But for the time being, there'd be no harm in just using MSIF for everything.
I see.
It's not very good for small integers, and it doesn't do elliptic curve or anything like that, so it's not suitable for a general
Yeah.
factoring algorithm, but it's okay if you just want to do quadratic sieve or number field sieve.
I assume your code is more readable or something also?
Oh, no, his code's very good. It's extremely
How-
well written in every respect, yeah.
Okay, better than
It's-
yours?
It's
Sorry to be blunt.
probably more readable. I mean, the recent version of the quadratic sieve is dramatically better than my last version. So I think
The recent version
our
of his.
readability is probably starting to
Okay.
approach similar sort of
Okay.
level. Yeah, I mean,
Thanks.
my first version of the quadratic sieve was spaghetti coded.
Mhm.
Part of the reason it's slow. So okay, so we also have some very basic beginnings of a Z mod PZ module, and also arithmetic for just basically C longs. That's probably not so interesting to Sage, but we can do a lot of arithmetic with pre-computed inverses. For example, if you just want to do modular arithmetic, we've got some primality testing. Well, I should really say pseudo-primality testing at this stage. I mean, it will test primes and prove it up to about 10 to the 15, I think. There's CRT, a Chinese remainder theorem.
Huh,
I've
interesting.
also added Scoof-Off, which is another factoring algorithm for smaller numbers, less than, say, 32 bits. As far as I know, this is the fastest implementation of Scoof-Off out there.
You should be able to use it for up to 64 bits. I mean, that's the whole point of it, right? I mean,
Well, you can use it for 64, but I mean,
Okay.
I've got another algorithm that will beat Scoof-Off
Okay.
between 32 and
because there is a
64.
spoof-off in SimPal.
Right. Yeah, well, you use a small quadratic sieve at a certain point. I
In
mean,
my
it's just not the optimal algorithm to use. So, anyway, the Scoof-Off that I've implemented is based on ideas of Wagstaff, and it's about 4 times quicker than the Parry Scoof-Off. So it's quite fast. As far as I know, it's the fastest. I don't know of any other implementations that approach that. But it's mainly due to ideas of Wagstaff. So we also have our polynomial arithmetic, and just to dispel the myth that we only have multiplication.
Let's have addition.
Well, the Sage wrapper only does it multiplication, doesn't have addition. That Robert wrote in like a half hour.
Because there wasn't an add function for managed polynomials.
Is there an add function for managed polynomials?
Yeah.
Okay.
Well, I've added
It's also
that. Well, actually, I haven't actually added managed function for scale and on DX.
Next is
Okay.
next for power.
Oh, exponentiation, yeah.
Next to power series. This looks
Oh,
No,
So when you
it's
told me-
powering a polynomial.
is that what you were telling me about earlier? Was
No, that,
Power
no, that
or-
was already there. That was
Okay,
powering
okay.
a polynomial. So power series multiplication, as of today, power series powering, and it's efficient. And
cool, very cool.
I will be talking about div today, when I get around to it. For just integers, we have fast integer multiplication. This is, what are we, 2.3 times faster than the current GMP, something like that?
For big stuff, yeah.
For big
Wow.
stuff, for very big stuff. I mean, it's only for FFT stuff, so once you get past about 100,000 bits or something like that.
But we've also
It's
seen
not so bad.
some development code that GMP has, and we haven't seen the code, but some profiles.
Yeah.
And they're catching up.
Yeah, well, I believe the graph was something like this. It's
Yeah.
FLINT and them. I mean, it's comparable to what will go into GMP5 in a few years. But
And
there's some,
Magma is
there's some
something like-
licensing issues with that, and I
Is that-
personally don't
Yeah.
think it's going to make it in.
The
quite some
version,
time.
the version
It's
of Magma
GMP.
on-
That's what them is.
I don't know that for sure, but that's what I mean.
The version of Magma that we have on stage at Methaman, which is about a year old, is pretty much neck and neck with the current GMP release.
Yeah,
Right.
Very close.
there was a long battle between Granlund and
Yeah.
Allen to see who get the fastest. And they,
Why are they battling instead of collaborating?
It would be really nice to know if they're just calling GMP to do
Yeah.
it by, making a version of by tracing it basically. Since you could link in your own version of GMP that tells whether it's being called.
Well, they're definitely not calling GMP for
collaborate with
FFT
anyone who's not a
modification.
Oh, okay.
Allen.
I mean,
They just happen to be the
they
same
use
speed.
it For shorter modification,
Uh-huh.
and that's part of
Okay, so you know.
the thing, yeah. Yeah, well, that's easy to tell because it's so much faster.
Oh, I thought you guys said it was the
Paul
same.
Zimmerman and Allen worked a lot
speed.
better.
So I missed that.
You said
No,
the
I mean,
GMP and Magma are the same.
Multiply integers faster than the current GMP.
You just said that
Not
they were
that
about
much
neck and neck.
faster, but-
I think they're pretty close.
Yeah, they're fairly close, but it's not the same.
No.
Okay.
Yeah, Magma definitely has the advantage there, but it's only a very small difference.
Yeah.
Maybe 20% or something. It's not
I see.
a factor.
So your fast int mult is beating Allen's right now.
Oh, it's beating both, yeah.
I see.
Yeah.
Are you talking about the tomb and encodes
Tomb.
for these multiplication Z?
I mean, this should be in the FFT
No,
range.
the term we're using GMP's too.
Oh, right, yeah.
Because
No, no,
there's like work by Quadrato and Zanoni.
Yes, and I've been discussing that with you actually. It's very interesting stuff. But that's in the region of a few percent faster.
Okay.
Two range.
Yeah, I've seen like the graphs and.
Yeah, that's like 4% or something.
Okay.
I mean, that's
Well,
that's
David has
still-
also implemented some algorithms which significantly
4%
speed
is
up
stuff you care about,
FFT
right?
calculations.
4% is something you care about.
Well, I mean, this Van Buskirk thing was 5%, but I don't know if anybody's ever.
Yeah, I think the exact quote was, we care about anything more than 5%. But,
Yeah.
Later on, I'm going to dispel this myth as well. Okay, so we have a very toy implementation of 3D factors and matrices.
What about 3D graphics?
Not graphics yet. I've actually been
Just
working on that as
offloading
well,
the
but
graphics
not
chip.
part of the FLINT project. So this has an LLL, like a floating point LLL. These are some of the ideas of Stella, but it's not going to be anywhere comparable to his implementation, which is very good, as Mark and I have been finding.
Well, you know, I mean, so these graphics,
Yeah.
the chips on graphics card are optimized to do certain things like rotations and things. Then you can offload everything to,
Oh, sure. Yeah. I
They
mean,
just don't
it's-
care too much about precision.
yeah.
Yeah, it
Yeah,
seems
you
to me
have to
that
be very
some
careful.
computations you could do most quickly by shipping off to your printer.
Well, yeah, if you put them in PostScript.
Well, it can be done. It happens.
A lot of computation can be done more quickly by shipping them off to name alkies, actually.
Yeah.
And while we're on the topic of name alkies, the reason I implemented this is because Samir Zigzag and I have been working on implementing an algorithm of alkies for computing solutions to this diphantom equation. And so we've found about roughly 100 new solutions. Well, for different values of k, you want very small values of k here, you know, typically in the tens or hundreds or thousands.
Is this beyond what a Yanel and a Elsenhans have done?
And what Dan Bernstein did?
Well,
I mean,
Dan Bernstein.
there was something maybe earlier this year that the Yanel and Elsenhans went and they found 33 or whatever.
Oh yeah, that.
Yeah.
I thought that's not the name I remember.
Oh, well,
Yeah,
I mean,
know the
maybe
paper,
I'm
yeah.
making it up, yeah.
Yeah, there were 4 guys from Georgia.
Oh, no, that's a completely different thing. These are, I think there are people like Goodington.
Right.
I
don't
thought it
know.
was Elson, Hans, and
Well,
Jano.
there was someone that did 30 or 33, I can't remember.
Yeah, I mean, they did 30.
Earlier
The
this year.
grad students did, I mean, slightly after you.
Oh, really? Someone's got the other one? I didn't know.
I don't think it was 33. I think, but they did a lot up to 100. I mean, they have.
Oh, yeah,
And
sure.
yeah, I mean,
Yeah.
they have like a 2-page preprint. And they just say, you know, we just.
Okay, I'll have to check and see if that's the one that I know about. But anyway, we've got about 100 new solutions. Obviously, they're not less than 100, but yeah. So that's why I implemented that, and it seems to work very quickly and seems to be fine. But I'm sure that there are better LLL implementations out there. But anyway, that's a short summary of what we have in FLINT to date. We're really only pre-releasing the polynomial arithmetic at this stage. And the other stuff really needs a lot more consolidation, testing, etc.
Except for QSIV, which is pretty
Yeah,
solid.
that is about to be released. I'll be releasing the new version of that shortly. It just needs some packaging of the results, of the factors. That's about all that needs to be done there. So that should be coming soon. Okay, so now I need to motivate why we want to
Can I
work
just ask
on.
a silly question? Does QSIV have a library interface, or is it just the command line interface?
It's
Command line.
a library.
It doesn't
interface
matter
now,
when it takes
but-
a data.
Sage
to do anything.
only interfaces with it though via the command line.
Yeah, at
Because the
moment,
overhead of, I mean,
yeah.
Yeah.
it runs a lot
Yeah, yeah.
longer.
It takes
Yeah.
1 day to run, so the overhead is
No,
Oh,
no,
you
no,
can
no.
factor anything down to
like
Like
20
40
bucks.
digits.
I mean, it's
Okay.
yeah.
Well, right, doesn't it have a restriction that the input has to have at least 40
this
digits?
is the new version I'm talking
Oh,
about.
cool.
Yeah, the new version
Cool.
is the library version, and you can.
I don't know if
factor
you want to
anything.
use it
Oh,
for
very
less than
nice.
about 25, and probably with your ECM, it should be something like 40. So, I don't know.
Yeah, well, ECM has other advantages than when you
Yes.
call the small factors. Yeah. So anyway,
Do you have GMP ECM?
EC2
Yeah,
was a part of
yeah.
the first case where
And in library mode
funds
and-
funds in the solutions.
Okay.
Just nice.
sorry, what was the name?
Well, let's see. So
It's on
by-
Schinkel's webpage. so
Yeah,
I
it's
found-
Andreas, Stefan, Els, Hans, and
and
you're
Jörg
Janel
Yes.
And they found 2 new solutions.
for 52, for which time was gone before, and etc.
Right. Oh, excellent.
And also new
Fantastic.
solution for 30.
Yeah.
Oh, good.
Schinkel was telling me about this,
Yes.
and Brandon.
Okay, so, right, so we need to motivate the next part of the talk. The next problem, or the next logical problem after polynomial multiplication is polynomial division, which for z-axis is not even clear what you mean by polynomial division. So we're a little bit crazy even implementing this, but we did anyway. So essentially, because you're working over a ring instead of a field, you don't, when you divide one polynomial by another, the remainder is not necessarily going to have a lower degree than what you started with. But you hope for some kind of normalization in the remainder. You hope that the coefficients, or as many of the coefficients as possible, are small. So the algorithm that we implemented here can be used just as well in the case where you're working over a field. And in that case, you will actually get a division algorithm and so on. I've just done it over ZX because that's what we happen to be working on at the moment in FLINT.
Is it with denoted by pseudo division, where you allow a scalar in front of
This
your numerator?
can be used with pseudo division, but it's not actually, it's not implemented yet. It's pretty much a copy and paste job, and we just have to keep track of the denominator, I believe. So, when you compare this, so this graph up here is a graph comparing NTL and magma. Now, I've been a little bit kind to, first of all, because...
Who are the good guys in this one?
Sorry?
Who are the blue guys?
Because it says
Is this
NTL
a
in
blue
red
state or a
and
red state?
it says NTL in red and
Oh,
magma in blue down there.
NTL
So
is red and magma is
Intel is
blue.
doing better in the red.
oh, okay,
Yeah,
I see.
NTL's winning.
So red's the bad guys and blue are the.
Hang on, who's
No.
the bad guy?
I don't know.
The
Red
blue
is
guys
always the
have the
bad
red
guys.
guys surrounded.
Okay, yeah.
Okay, in any case, red is NTL.
The coasts are blue, right?
Yeah, yeah,
Interior is
yeah.
red.
Yeah, so I think NTL,
Yes.
NTL is winning here and magma is winning here. So this time the
Bush is winning.
well, I don't know who's the bad guys. I mean,
Yeah.
They're all not you.
They're striking.
The closed source as compared to the open source. I mean, that's what it boils down to. So anyway, this graph clearly shows that magma is winning in a significant portion of the graph. And just to give you an idea of the scaling here, that's a factor of 5. So it's really significantly faster here, as is NTL up here.
That's also a factor.
You just
That's
switched
also
to
five.
identities
Yeah.
again. NTL is red, I thought.
Yeah, NTL's red.
I'm sorry, other way around. Yeah, so magma is 5 up here, and NTL as well, maybe close to 5. So this is a significant.
Which
difference.
NCL division routine is this?
This is just divide. So let me explain this. At magma, if you do ordinary division in magma actually implements division for ZX in exactly the way I described by normalizing coefficients. However, it is incredibly slow, glacially slow. I mean, the profile would not have finished if I started it running when I began coding this. It's just not feasible. However, what you can do is coerce your problem from the integers into the rationals and get magma to use its very fast rational arithmetic, so long as your answers are going to be the same. So what I've done is fed in this case, exact division. So I know in advance that the quotient is going to be exactly something in ZX, just by multiplying two things in ZX and then doing division again. So that's fair to magma. It means that we can compare against their fast algorithm. And NTL already has an algorithm for dividing. And what it does is it checks, and if it's not divisible by the thing you're dividing by, it just returns 1, says this is not divisible. If it is divisible, which is going to be the case always here, it completes the division and actually returns the quotient. So it's fair on both sides. It's a fair comparison of algorithms. The only slightly unfair thing to magma here is that they're probably using pseudo-division because they're able to divide general polynomials over the rationals, and there's a little bit more overhead in keeping track of the denominator. I mean, the denominator is always 1, but it's just slightly unfair in NTL's favour here.
Is there some command in magma called something like exact divide or?
I haven't found
I
one.
thought there
did look
was.
for one. If there is
Yeah,
one,
I thought
There's
there-
exact quotient.
Yeah, exact quotient, because Mikhail Stroll uses that all the time.
Right, but I think
What's it
that
called?
just does a long division and returns an error if the remainder isn't 0.
Okay,
Right.
okay.
Well, I should look into that. Maybe I've been very unfair to magma.
Who
But
knows?
What
I'm
about,
pretty sure. that there's-
what about division over large, or for that matter, not so large finite field?
we don't have anything implemented for finite fields at this stage.
Not even prime finite field?
No. I mean, we've just started implementing FLINT.
We equals Flint.
Yeah. Yeah. Oh, you're talking about magma? I mean, magma certainly has stuff for finite fields.
And NTL and magma should both have some.
Yeah, NTL and
Yeah.
magma both have. I mean, this FLINT is the package I've been working on, but this is a comparison of NTL and FLINT. So I'm sort of comparing
Yep.
the best open source with the best closed source.
You just said NTL and Flint, but you meant to
Sorry,
say
NTL
NTL.
and magma. Oh, goodness. I said sage. No, I said magma instead of sage.
So there's no fleet.
Anyway.
Right, there's no Flint.
No, not yet.
No.
We eagerly await a slide like this with Flint.
Exactly. Right, okay, so it's a bit difficult to put
Probably.
three columns in
That's,
the same.
yeah, that's what I meant.
Anyway, I don't think I'm going to have that much time to talk about the algorithm. I'm just going to summarise what I was going to say. I've spent really all the time talking about pretty pictures. So essentially, what you can do with division is you can essentially do a kind of divide and conquer approach with division in a similar way that, for those who know, the Karatsuba method works for multiplication. The reason that I even started thinking about this was because of a news group post on the internet from John Cannon from circa 2000, and someone was comparing the speed of magma and Parry at doing a particular computation over in a finite field where the binary representation of P was sparse, and magma just amazingly blew Parry out of the water in this particular case, and people were sort of wondering why is this so. And John Cannon made the remark that magma uses a divide and conquer approach for division. Now, I misunderstood what he meant, and I thought he meant polynomial division, so I started thinking about whether it's possible to implement this polynomial case. And I'm sure magma does. I mean, it's a simple step to go from one to the other. The algorithms are often related. And so I sort of came up with a divide and conquer algorithm, and later discovered that I'd rediscovered an algorithm. So essentially it works like this. If you have a dividend and a divisor with a leading coefficient here, classical multiplication simply runs along, and all you're interested in is dividing this leading coefficient into the coefficient that you happen to be up to, and you get a quotient, which you'll put here. Then you'll run through and multiply this quotient by your entire b, so you're only doing a multiplication there. Put this down here and then do a subtraction. So you'll simply take away what you've got so far from the original quotient. The original dividend. Now, divide and conquer works in a similar way, and it's really quite simple. Instead of taking a leading coefficient here, you just take a leading polynomial. And other than that, the algorithm is very simple. It turns out that you end up dividing your A into 3 pieces, or at least the way I do it. This is how it works. So let's call this B1 and B2.
Which is B1?
The one that says B2.
Sorry. And what we'll also do is we'll take the same B and we'll divide it the other way. So if, for example, B2 is shorter, we'll call this B3 and we'll call this B4. So it's the same data, we've just divided it in different places. Now let's just suppose that the length of B1 is N1, and that's obviously going to be the same as the length of B4. And we'll call the other length N2. So it turns out that you can do something like this. Cut off a piece that's length N1, cut off a piece that's length N2, and cut off a piece that's length N-1, where N-1 is the length of the whole divisor. Now, I'm obviously simplifying this for the purposes of exposition. You're not necessarily always going to be dividing something of length 2n-1 or something of length n. That's just how the algorithm works at best. In practice, you have to pad with zeros or something here, and maybe this is too long, so you have to break it up first and so on. But essentially, this is how the idea works. And the idea is to follow exactly the scheme of the classical division algorithm, just considering this to be your leading coefficient. So let's give these names A1, A2, A3. So the first step will be to take the quotient of A1 shifted appropriately by B1. And so that just looks like this. So that's essentially equivalent to your step to get your quotient here. The next thing that my algorithm does, obviously when you're doing a division problem, you can return a quotient and a remainder. It's equivalent to return the quotient and the product of the divisor and the quotient. So what I'll do is I'll have an algorithm which will return the quotient Q1 and the product of the original divisor and the quotient. If I want to get the remainder, all I have to do is subtract this product from what I started with, and that will give me the remainder. So that's the general idea of this step here. It's equivalent to doing a full division problem. The second thing we do is we do a computation, so we actually compute B2, so the rest of this divisor, by Q1. And we can use fast multiplication. And this is really where the saving is in this algorithm. Here, you have to do scalar multiplication every time because you had only a single quotient coefficient and you were doing a scalar multiplication. Here, you're doing multiplication of polynomials, and there are much faster algorithms for that. The second part of this, obviously we're only halfway through the quotient that we want to do. We've only really dealt with this first part. So the second part is to, well, first of all, we can construct B, the whole of B, times this quotient. It just turns out to be this. So this is just an addition, basically. So that's cheap. The second part is to get the second part of the quotient, which would sort of correspond to...
Q1 at the end of that?
Sorry?
Q1 at the end of that.
This is... sorry, it should be... Yeah, you're right. Yeah. So the second part is to get the quotient of this by B1. You're sort of moving along as you would do in the classical algorithm, but you've only got 2 steps here. And essentially, all we have to do is to shift A2 appropriately and divide by B1. But there's a convenient way that we can do this. We can take all of this and subtract the product that we have so far. And it just looks like this. I mean, you have to work through the algebra to make sure this works. But we take this product and we subtract it from this part appropriately shifted. And my observation is that the first N1 terms are 0. I mean, obviously in practice there are savings you can make in the implementation itself. So essentially what we've done is we've done a quotient to sufficient precision to cancel out all these terms. I'm assuming here I'm working over a field, I guess. If it's not a field, you won't get zeros here, but you can just ignore whatever you do get. It's not relevant anymore. Okay, so the final step is to do the actual quotient that you need. I mean, there's nothing, I haven't actually done anything here except a subtraction. So this is the next part that has any complexity. Let's just call, well, I just call it T just to save explaining anything further. I'm going to divide this T that I end up with by now B3. So I don't need to, I only need precision of N2 coefficients. I'm doing an N2 by N2 type thing. So I only need the first N2 coefficients here. And I mean, if you think about this in terms of power series, it actually makes more sense. But, and of course, I said that my division algorithm is not only going to return the quotient, it's going to return the product of the divisor and the quotient. So I'll get that for free, presumably, if I implement this correctly. Finally, I have to do the computation again of B4 Q2, and again this is fast multiplication. So you can see I've replaced all of these scalar multiplications that I would normally have with just 2 fast multiplications here and here. And I've got just 2 polynomial quotients which can be done recursively. So I'll call this whole algorithm again to do each of these. And I can now construct the BQ2, just by addition, that's just B3Q2 x to the n1 plus B4, and both of those quantities I've actually computed. I've got B3Q2 here.
B4Q2?
Sorry, yeah. And B4Q2 I've actually computed by fast multiplication. So it's just a matter of adding those. I get BQ2. And it all drops out because the quotient that I require is just Q1 x n2 plus Q2, and finally BQ is BQ1 x to the n2 plus BQ2. So what I've done is I've got a new algorithm. It takes as input A and B, which are polynomials with the given lengths, and as output it will give me Q, which is A div B, and the product BQ. So that's what this algorithm does. And it's a recursive algorithm in that that was what I was required to do at both of the quotient steps here and here. And so you just iterate down to the bottom until you get to some limit, and you just swap over to classical multiplication, classical division over at the bottom. That's basically how it works. Now it turns out that this algorithm was already existing in the literature. It's difficult to attach a name to this. I think it's been rediscovered more than once. In the case of integer division, the name's Javelin, I don't know if you can pronounce this, I have no idea, is associated with it, and also Bernickel Ziegler, according to Paul Zimmerman. But I haven't got a reference for that yet.
Yeah, that's research report at MPI, Saarbrück in October 1998.
There you go.
Was that a setup?
Fast recursive division, it's called.
Wow.
No, it wasn't.
It's
So-
in Zimmerman's paper.
Oh, was that?
It's in Zimmerman's paper.
Oh, yeah. it's
But you just
certainly
happen to be
in
reading right now.
It's also in his MCI, modern computer algebra. Arithmetic, perhaps. Was there a question?
Yeah.
Okay, so now the question that I'm interested in here is to do a quotient. I'm only interested in the quotient. I'm not interested in the remainder at all. And so the question is, can I somehow or other save time if I don't require this? And the answer is yes. Obviously I don't need to do that computation. And this was only used for that, so I can cross that out. That was used only for that, so I can cross that out. In this Q2 here, let me see, I actually have all these circled so that I don't get lost here. Yeah, I don't require B3Q2. And so essentially you can cut a lot out of this algorithm, and you'll notice now that all I require here is just a quotient. I no longer require a remainder or a product. And so if I drop the condition that I need this at the top level, I don't need it here at any of the steps below. I still need the full division at this first step, however. So I have to implement both algorithms, but there's still a considerable saving in doing this. And this algorithm, which I've just described here, is called Mulder's short division algorithm. This is definitely contained in a paper by Mulder's. Sorry, this should be Mulder's. And he attributes it to basically the Javelin, where he only did it in the integer case. Now I looked at this this algorithm, and of course we don't want to just implement the best algorithm out, but we want a better one. And I realised that you can make even greater savings here because you only need the left half, if you like, the top half of the coefficients of this product. And so the question is, can you use a truncated multiplication somehow to save any more time? And the answer is yes. Obviously not going to go into the details, it would take too long. But the essential summary here is that Mulder's short division requires a full division, what we might call a full division at the first step here. It requires what he calls an opposite short multiplication at this step where I say compute. And he requires a short division. I mean, these are the steps with any complexity anyway, short division back here. What I replace this with, try not to fall off here, what I call half division, which is essentially where you return the quotient and only half of this product that you would normally get, the top half of that product. I still require, let me see, and yeah, opposite short multiplication, so that hasn't changed, and a short division. And now the whole algorithm only returns the short division. So in other words, a division without remainder. And the only thing I have to explain is how to get a half division, and this is simple. A half division is broken into a half division, a full multiplication, a half division, and a full multiplication. So it's considerably less expensive than a full division, which had 2 full divisions and 2 full multiplications. So you save quite a lot in this algorithm, especially once you iterate, recurse down to the point where you cross over to the classical algorithm, where really half divisions save you quite a bit of time. So with these extra improvements on Mulder's algorithm, we save about 15% roughly, time-wise. There's a further trick that we can use, and this is already in Mulder's paper. We can alter how far along we do the division here. For Mulder's algorithm, it turns out the slap bang in the middle is pretty much optimal. For my algorithm, it turns out that you have to shift this quite a long way across. So that's another.
That was the whole point of Mulder's paper, right?
That was the original point of his paper, but it was for a multiplication algorithm, not for a division algorithm. He said he simply had a very short paragraph saying in the case of division it doesn't work. It's essentially the gist of it.
Zimmerman did it for the square root, actually.
Right.
So he didn't get it was equally split.
So the idea is somehow that if you look at the computation tree, if you go down the recursion, then like there are actually quite a lot of the nodes are actually the bad divisions, but then you make the lengths of them shorter and put all the work into the half divisions and short divisions and
That's
stuff.
essentially the idea.
Yeah.
So I guess the only thing to do to conclude is to show the comparison. This is all implemented in FLINT. Let's see. So let me first give the comparison with Magma. So this is a comparison of FLINT division with Magma's fast division in QX. And it's actually not very clear here, but there is some red in this region here. So for 10 bits or less, you should use Magma. 10 bits or less until the next bit revision of FLINT. The scaling here is a factor of 5. So we're really quite a long way ahead for most of this. And I think this is actually a tuning problem on my part. I haven't actually had much time with this algorithm to clean it up a bit, but that's probably a tuning issue. Okay, so finally the comparison with the best open source implementation. We're talking about a factor of 25.
Dang.
NTL does win here though, so if you are multiplying one by one, then I suggest you use NTL.
Dividing over.
So those vertical bars there, I think, and it's NTL doing a multi-modular small prime FFT.
Yeah, it looks like
That's
it.
why you get those bars.
Yeah. It's interesting actually that it doesn't do so well in that region. It's kind of weird, but
That's where it should do really well, yeah.
yeah, you'd think so, but it's just not a good algorithm. I mean, I think essentially this approach can be used in the finite field case, and then you can use multi-modular algorithm. It'll probably beat it by even more, but it works in the far edge.
Any more questions? No, let's thank the speaker again now.
5 minute.
5 minutes, yeah.
Yep.
And then Mike's session?
Yep.
Yeah.